to announce the visit of Dr. Gyula Jozsa. He's on his way to observe with the INT telescope, so he decided to make a stop here in Tenerife to give us this presentation. So thank you very much. Dr. Jozsa is Hungarian. He's an Hungarian astronomer, but he grew up in Germany. So as he told me a few minutes before, he is 90% German, actually. He obtained his PhD in 2006, so he's a very young astronomer, actually, at the University of Bonn. Later, he obtained a postdoctoral position at the Radioastronomical Institute of the University of Bonn, but this institution has recently changed its name to Argelander Institute for Astronomy, IFA. So very recently, Gyula has moved to the Netherlands to work in the Astron Institution, which is a radioastronomy institution in the Netherlands. Actually, Gyula is a support astronomer of the Westerbork Synthesis Radio Telescope, working in radio wavelengths. So thank you very much for visiting us, and thank you very much for giving us the talk.
First of all, let me thank you for the invitation. It's an honor to be here. I will talk about warps in galactic H1 disks. There's a lot of expertise here on warps. I'm aware of that. Thus, I will mainly focus on the H1 aspect, what we can learn with that. Let me give a brief outline. First, I will talk about the history and possible formation scenarios of warps. Then I'll tell about some H1 observations of symmetrically warped disk galaxies and one extreme warp, which is NGC 2685. Well, first, the definition of warps. Warping is a large-scale bending of a disk. This is a warp. And brief history. Some redshift galaxies were for a long time, but they were usually considered as being awkward galaxies. And the recognition that warps might be something important came with the discovery of the Milky Way warp quite early in H1. And then investigating nearby galaxies in H1, Wright et al. Gave the first correct interpretation of these wings appearing in H1 maps of the nearby galaxy M33 as being due to a warp. Now, at this time, people thought this could be anything, so people didn't quite believe. But then Sanchisi in 1976 showed undoubtedly that in H1 galaxies there would be also these features seen, which undoubtedly were warps, bending of the disk. And then when Bosma in 1981 in his famous work, published his famous work, he could show that warping is important appearance in galaxies indeed. But there's a few simple shapes that you might consider for warps. There's the S shape or grand design integral assigned warp, the U shape. These are the very simple appearances, and the L shaped warp as a combination of both, mostly thought as a combination of both. Going in the description of warps somewhat into more detail, you can introduce modes, so that you consider the disk of a galaxy being a superposition of modes with a certain amplitude each. But I won't go that far. Now a bit about warp statistics. You know much more about that than I do, because this is mostly done in the optical. First thing, warps are ubiquitous. At least 50% of all observed warps, of all observed disk galaxies are warped, which means that in principle it's a phenomenon that you can observe or that is probably present in every galaxy to some extent. And this shows, the next point is that warps start where the optical disk fades. And this explains why warps were first established as a common phenomenon with radio observations, because only in the 80s, 90s, optical telescopes became sensitive enough to examine warps in the optical regime. So this is what you see when you have an optical sample, slight warp, while in H1 it is much more pronounced. Most warps are dominated by an m=1 symmetrical shape, and they tend to become more symmetric in looser environment. This is already telling something. The proposed generation scenarios, of course, involve satellite interaction, and now there is a problem. You have a satellite at some distance, spiraling in. The problem is to transport the angular momentum to the disk. The warping energy contained, the angular momentum is high enough, but you have to transport it. Now this seems to be solved. You can induce wakes in the dark matter halo, use the dark matter halo as an agent to transport the angular momentum towards the disk. Or, if you like this more, you can use the far field effect of MOND to transport the angular momentum. Extragalactic winds have been proposed. If you have an extragalactic wind imposed on the disk, you can impose also a torque on the disk, not only a linear momentum, but also a torque. On the other hand, you need quite high gas densities. Even if you consider direct infall onto the disk, you still need quite high gas densities, and on top of all, you produce usually asymmetric warps to some extent. Magnetic fields also require quite high magnetic field strength, usually only found in clusters of galaxies, and probably cannot stabilize a warp. Now here you see a picture of the Milky Way warp, which is asymmetric. But this is a quite interesting case. Galaxies found or thought of as being in a loose environment have these tidal features around them. It's actually from this institute here. The overlay is made by George Heald from our institute using archive H1 data. So this might have to do something with the generation of warps. But the point is, the big interest lies now in symmetric warps, because they are the ones that are found in a loose environment. In a dense environment, we can produce warps, asymmetric warps, quite easily. But this predominance in loose environments suggests that that either these symmetric warps are long-lived, so m=1 modes are long-lived, or there is a frequent excitation that is different from the excitation in mixed modes. Now, in radio astronomy, using the H1, we have the possibility to make this kind of tilted ring model where the galactic disk is thought as to consist of a set of rings, parameterized by two orientation parameters. then you have, of course, the central position. And you apply rotation velocity. This is especially interesting because a grand design symmetric warp is a coupled gyro. Imagine you have a disk that is warped, then the disk exerts a torque on itself. If you then have a dark matter halo in the whole system that is not necessarily spherical, then also this exerts a torque on the disk. And but the whole thing is quite complicated system of coupled gyros. And now to explain a warp as a long-lived phenomenon, you have to prevent, in principle, the winding up of warp. Because in this system of coupled gyros, the precession frequency varies and is not necessarily equal at all radii. This means that winding up of warp is a phenomenon that you have to prevent, theoretically, if you want to explain warps as a long-lived phenomenon. Now, if you have a tilted ring model, you have a tool to investigate the precession. If you have a precession, a co-precession, then you can have a look at the line of nodes. The line of nodes is the line of where the disk material has the systemic velocity of the galaxy. The tip-lone plot is a projection of the disk or of a spin normal vector of a ring onto some reference plane. And as you can see here, if you have differential precession, then if you have a look at the line of nodes and the tip-lone plot, you see some bending in the regions where there is no co-precession. So co-precession is present if a reference plane can be found in which the line of nodes is straight. So this tool has been used by Briggs to investigate the structure of some one or two handful of galaxies, and he found his rules for the behavior of warps. Now, what I have already told is that the H1 layer is planar within the bright in the range of the bright optical disk, and then you find a transition radius where the warp starts, but still the line of node is straight, and the warp starts beyond R25, and at the transition radius, the character of the nodal line shape changes, becomes a leading spiral. So it advances in the direction of galactic rotation, and then there's the fourth rule, which I always call the forgotten rule. That is, a unique reference frame exists where the line of nodes shows two straight regimes. In principle, if you take this seriously, this means that there is two regions of co-precession, one inner one and one outer one. Although Briggs later on retreated from this statement as being due to projection effects. But we will see. So in the light of this study, the so-called modified tilt modes, where a warp is explained as a bending mode in the presence of a either inclined flat or round halo, can be ruled out. Furthermore, it has been found that the disk-halo interactions play a great role. If you have an inclined halo with respect to the disk, then you can produce, in principle, a mode, a frozen-in warp. But if you have but the halo and the disk can exchange angular momentum, and what happens is that the halo falls onto the disk. And in principle, the warping force is destroyed within 1 or 2 revolutions. Late cosmic inflow does seem to do a good job. This is a Diplon plot produced in a model by Shen and Selwood, who investigate how the disk reacts on a ring of dark matter or a ring of particles where that exert a torque on the disk. And what happens is that you find that the retrograde precession slows down when we get outside of the disk, but then speeds up again in the range of this ring. Now you can take everything that exerts torque. It doesn't have necessarily to be a ring. But then you would find this breakthrough that you have an advancing line of nodes. So currently this makes a good job. So what we did is we took a few H1 galaxies or very symmetric H1 disks and investigated their structure in terms of the tilted ring model, but first we had to solve a problem. The problem is to construct a tilted ring model in the presence of a warped disk. Now, what is usually done in such investigation is that you construct a velocity field. If you have a data cube, this is the intensity independence of frequency, and via Doppler shift, this is velocity, and the position on the sky. So for each position on the sky, with having a data cube, we have a spectrum. From this spectrum, one can derive a velocity, which is the recession velocity of the central plane. And from that, one can infer a tilted ring model. Now, this is fast, but the problem is that important parameters are missing. So if you have a velocity field, derived tilted ring model, you don't have information about surface brightness. And the most important thing is that if you have an inclined disk that warps, then you can have position where the disk crosses, where the line of the side crosses the disk twice, which means that you cannot assign a velocity. Now, the alternative is to produce a tilted ring model of using the data cube. And this is what we have been going on about for a while. Now, this is how it works. You have the tilt string parameters. You construct a cloud of point sources projected on a model data cube. Then you convolve it with a 3D artificial observing function. What you then have is an artificially observed model data cube that you can compare with the observed data cube, and in a loop, and from that you can evaluate some measure of the goodness of fit, and make a loop to make the fit better and better. We tested this. This is a data cube. So here, this is velocity. Velocity increases, and on each velocity, the intensity varies, as you can see. We tested it taking a model observation, adding artificial noise, and trying to fit this, and this worked pretty well. We could show that we can model galaxies with large warps, which cross where the line of sight crosses the disk twice. We do usually in a better job than the old method. And also there's something, we have an enhanced sensitivity. Because this is an integral approach, we take into account more pixels, or we take into account many pixels to derive the model. And actually what we can do is fit below the noise. Now we have the means to do our tilted ring models, and I pick now one of the objects that we examine. This is NGC 5204, a galaxy of Magellanic type. And the special thing about this galaxy is that it has an extremely symmetric H1 disk. This is what we got when we applied our software to the data cube of this galaxy. Here, this is the total intensity, this is the velocity field, and the comparison with, of the original with the model shows that we reached a quite good fit. This is a position velocity diagram. So going from here to here, we go along the green line from here to here, also showing that we make a quite good fit. Now this is quite interesting. This is gas that doesn't follow the expectation of a uniformly rotating disk. This is so-called anomalous gas. I won't go into detail here. And this is the model. What we see here is the surface density, rotation velocity, and these are the two orientation parameters, inclination, position, angle. And here you can see the warp, because here is a change in these orientation parameters. And what we also observe is a drop in surface density. And also in the rotation curve, we see a change. So, wow, this is something new. But first, let me go on about the geometry of this object. Now, these are the Diplon plots. Here, the reference plane is the inner disk, and we observe the advancement of the line of nodes in galactic rotations. These data points have large errors. But also, we can see that this, the forgotten rule 4 of Briggs is observed. We can find a reference plane where we have two straight lines of nodes that we observe for this galaxy. Now we wonder why. If you draw your attention to this diagram, it shows the orientation of the disk with itself at different radii. So if you want to find out what orientation a ring at this radius has with respect to a ring at this radius, you have a look here, and there you are with about 40 degrees. This is why this diagram is symmetric about the origin. Now, regions where the disk is flat are the bright regions where the mutual inclination of the disk with itself is low. Now, this is the flat inner disk, as we expect. This is a flat disk, which we didn't expect, which is outside. So this diagram shows, which is reflected also in a clustering of points here, that this galaxy, this is an opaque model based on the tilt ring parameters, has apparently a flat disk in the outskirts. And we observe this for all our galaxies. Are these news, we may ask? And to some extent, yes, in some other respect, no. Briggs rules are confirmed, also the fourth rule. And we showed that at least some galaxies show a two-disk structure in the H1 disk, the warping transition, from one orientation to the other. We are not alone. This has been observed before for single galaxies by Kuiken, Corbelli, and Schneider on M33. And also, we observe this at this transition, the rotation curve makes a change. Now, this is the fitted rotation curve. I am not sure that this reflects a real rotation curve in the sense that this reflects the potential. But it reflects a change in the physical structure of the galaxy. That is for sure. And at the same point, the surface density grows. Now, this cutoff in the surface density has been reported before using a galaxy sample of Garcia Ruiz by van der Kraut, who connected this to a truncation of the disk in stellar light in these galaxies. So we observe the same. Also, van der Kraut reported a drop in the rotation curve, which would then belong to a drop in the mass density in these galaxies. We cannot report the same because for our galaxies we have a rise in the rotation curve. Nevertheless, the change in the rotation curve is an observation that remains. Now, what does it tell us? It seems that we have two regions of co-precession, and even, which is the stronger statement, a flat outer disk. Is this reflected to some extent in theory? Well, up until now, bending moons have been examined using only rather stiff halos. So, but what if we change this a bit and assume that we can have a common bending mode of disk and halo, which means that the halo itself changes its structure with increasing radius. But then we might have a more complicated system that might still explain warps as a long-lived phenomenon. Late cosmic infall I discussed before. Shannon Selwood predict, in principle, this advancing line of nodes, but then at very, very large radii, they predict the twist in the line of nodes. Well, I'm not sure. Perhaps this is within the errors, but right now I would say this is not in agreement with our observations. Now, there had been a paper by Balin and al. Simulating the development of a galaxy after a last major merger. And what they find is a two-disk structure. Not only in the disk, they find a halo structure that is twisted. Towards the center, the halo is more spherical, while towards the outskirts, the halo changes orientation. Well, more spherical, but still has an angular momentum. And then to the outskirts, it changes its orientation. Now, if there would be a thin gas disk tracing this halo shape, then we would observe exactly what we see here in our observations. A thin disk that is rather planar. So let me summarize. First part, symmetric S-shaped warps are the most common ones. Either they are long-lived or frequently excited, and but then differently from the mixed modes in denser environments. We confirmed all of Briggs rules again, also the fourth one, which is a consequence of having a flat outer disk, that we observe for some galaxies. Then we see the indication that indeed the physical conditions change at this transition radius, where the orientation of the disk changes. Concerning theory, we can state that infall models do a good job, but, well, there's something that needs to be tuned there. I think the orientation of the halo and the flattening of the halo, so the internal orientation of the dark matter halo is important to solve this problem. So, and which might hint to the fact that warps might be, or symmetric warps might be explained at some point as a common bending mode of disk and dark matter halo. Which leads me to the second part of my talk, which is about a special polar ring galaxy. Now, polar ring galaxies are galaxies with two distinguished rotating subsystems of similar size, with, and this is important, orthogonal angular momentum vectors. Usually they are thought of being the result of a merger or a capture of material on a polar orbit. If it is a merger, you have to have a slow merger where two disk galaxies merge into each other, and the one gets stopped in the other galaxy. The interesting thing is the study of their kinematics allow, in principle, to find out or to constrain the 3D geometry of dark matter or overall potential. Since dark matter halo flattening is expected in standard cosmology, this is of special interest. But only a few confirmed cases are known. But nevertheless, these galaxies are interesting, as said. One of the confirmed cases, let's put it like that, is NGC 2685. Here's an INT image. Now, this galaxy is of medium size, consists of an inner lenticular stellar body, albeit it has an Devacouleur profile. Then what you can see is here this helix covering the northeast part of this galaxy, which gave the galaxy its name, Helix Galaxy. It contains gas, dust, and stars also, and has been shown by Ulrich to be rotating. By photometric studies, it has been shown that it is quite old, and this is surprising, because you would not think that such a structure is long-lived, but it is. And then what one can see is an outer stellar and gaseous ring. Now we observe this deep H1 and also optical observations, and this is what we see. These are I-band observations with INT, and H1 observations. This is high resolution, this is low resolution. And what one can see is that the outer ring, for the outer ring, all the substructures here, there's this hook in the north. In the H1 you can see it too, fuzzier at this edge in the H1 too. So this suggests that both structures, so this outer ring, belong, so both reflect the same structure. Both belong H1, and stars belong to the same structure. What we also observe is this extended H1 disk in the outskirts. Now we have this nice program. We try to model it, because in some respect you can also model polar ring galaxy as a tilted ring model. We first tried to do it like this. We call it flip model, and got this as a total intensity. Now, it doesn't match the observed total intensity very well, as you can see. We have here an edge brightening in the model, which consists of two rings. Well, we cannot see this here. The brightening is rather at the minor axis position of the outer ring. Here, the ring is very pronounced. It's not here. So we thought we should go on a bit and try the next simple model, which is a warp. What we can see is that with this warp geometry, we can reproduce only in projection the appearance of this H1, this H1 component of the galaxy. So here, these wings here are pretty well reflected. Also, the dimming at the edges. So this does a good job. But of course, I mean, this could be spiral arms or something. What really convinced us was when we took spectra on certain positions. Now, again, these are position velocity diagrams, which means that we take spectra going from this end of the line to this end of the line. Then we go from here to here. And for each position along this line, we observe the spectrum along this axis here. And what we can see is that, for the flip model consisting of two rings, and this position here, there is no H1 that we would detect. While in the warp model, because the disk changes orientation gradually with radius, and this enhancement here is a projection effect, this is also reflected in the spectra. So here we observe this H1 at these velocities as in the original model. Well, so this seems, at least to us, a bit more plausible. Of course, we model it, and this is what we got, a very good match of observation and model. This is the opaque model again, and this is what we observe. A surface density profile, quite normal for, say, a spiral galaxy, a flat rotation curve, and this reflects the very pronounced warp towards the center. Now, if we take a look at the rotation curve, we see it is quite flat. Now, if the halo of this galaxy would be flattened, since we trace the potential on different orientations with respect to this potential, or not dark matter potential, I should say, overall potential, we would in principle expect that the rotation curve shows a change. It doesn't. So what this indicates is that the overall potential is rather spherical. Another indication is the age of this structure. As I said before, photometrically, the age of this helical structure, where the H1 belongs to, is 2 to 6 gigayears. If you want to maintain such a warped structure for such a long time, at least if you neglect self-gravity of this structure, you need practically a spherical potential. You can do such calculations, simple calculations, assuming logarithmic potential or something similar. So I wouldn't insist on this. Of course, dedicated simulations, computer simulations, are necessary to verify this. But at least we have an indication that this, at least, is spherical, a spherical potential towards the center of the galaxy. For the outskirts, we cannot say this, of course. So, and this is already coming to the end. NGC 2685 consists of a lenticular stellar body. And on top of that, a heavily warped disk containing dust, gas, and stars. It's younger, but not too young. We observe no obvious signs of deviation from circularity of orbits, which indicates that the overall potential is spherically symmetric towards the center. That is, this thing is nothing special. What is special about this galaxy is rather the orientation on which we see it. There's other cases known of very heavy warps on top also of a disk. NGC 3718 is a famous example. So there might be more cases like this, or there are more cases like this. Now, searching the literature, we found an indication what this might be. Could be a remnant of a wet merger. Now, Nabedal simulated these wet mergers for some extent, and what they found is indeed centrally warped galaxies or warped gas disks that maintain or are maintained in the center of these galaxies for quite some while. Well, not 2 to 6 gigayears. This is in the limits of their simulations, but setting up this is possible. So there might be also a physical explanation for this. And with that, I thank you.
So there's time for questions. Okay.
So in this galaxy here, do you need or want the warp itself to be stable in time? And if so, have you tried any... In this galaxy, do you need or do you want the warp to be stable in time? Or can it be a transient feature? And if you want it to be stable, have you done any kind of modeling to see whether the whole structure can be stable? The whole galaxy?
No. We haven't got that far. So the age of this whole structure is from photometrical point of view 2 to 6 gigayears. If you do very simple calculations of the precession rate, see towards the center of this galaxy, precession rates vary a lot if you have an aspheric potential, which means that this feature should be very transient. But it ain't, because it has a large age, basically. That's the point.
But what exactly has the large age? Because the warp, as in your model here, that's a gaseous warp, is it?
Yeah, but it's also reflected in the dust planes, and the dust planes contain stars, not only young stars. Or not the dust planes contain, but there's also a younger population of stars that is contained in the helix, but it's not that young. That's the point.
About the first part of the talk. When you talked about the mechanisms to create warps, you said that the accretion of intergalactic matter onto the disk produce asymmetric warps. Indeed, it produces both. It can produce symmetric or asymmetric warps. It is not always true that it is asymmetric. It depends on the inclination on the wind which comes onto the disk. And this also comes to your conclusions about why there is this drop of the density when the warp begins, or the rotation curves. You are based in the case in which the halo of dark matter is the dominant mechanism to produce the warp. So you are using the Bini model in which the accretion is produced into the halo it produces the misalignment of the halo with the disk, and this producing the warp. You are taking into account this model, I suppose. All the conclusions that you mentioned at the end when you talk about the role of the halo or the dark matter rings, you are assuming that the dark matter and the halo is taking an important role in the formation of the warps. But it is also another possibility that there is no necessity of this dark matter halos or dark matter rings. It is also a possibility that the accretion of intergalactic matter produces the warps also, because the accretion of intergalactic matter onto the disk can produce also symmetric warps. So the explanation will be different in such a case, and there will be not a connection with the dark matter.
Yes, I think this is something, of course, to investigate. I thought this question would come. The point is that I think this publication that you have to have a special orientation of this, say, accretion onto the disk, direct infall. Very nice idea. I mean. Just to explain what we expect is a sort of mode of cold accretion. That means that the disk itself can be affected by it, or can get a torque. Correct me if I'm wrong. Just from infalling matter. Now, the question is whether the frequency of very symmetric warps could be explained by that, and also, I think it was mentioned in this work by Sanchez Salcedo, whether indeed the gas density would suffice to produce warps of the amplitude as I have shown here. Because these are really large warps, and we don't know much about the common amplitude in the gas, because there's not so many studies of gaseous warps. But this amplitude is rather high, I think.
We can discuss later, because
I won't.
But the answer is yes, the amplitude is plausible, and the frequency of asymmetric warps is relatively low. So the prediction is that the symmetric warps are most of the cases, and there are few cases in which there are U warps and L warps too. So
I know the work, but there seems, correct me if I'm wrong, some disagreement between you and.
More questions? Okay.
Well, for the second part of your talk, when you talked about the polar ring galaxies, during the simulations which you did in order to explain observed feature, did you try to put...
We didn't do simulations. We made kinematical models.
Just kinematical models, okay. But did you try to estimate what the time frame can be in order to get this picture, or it was never the purpose, it's just a static? The idea is that to see how stable can be the polar ring, for example, for NGC 4650A, or that.
So this is a study of an individual galaxy, and we turned, in principle, the argument around. We didn't argue that the polar ring, or kind of polar ring, is stable. We calculated, in principle, to what limits and ellipticity of the potential can be allowed to still have this potential. And the time scales are given by the age, in principle, of the stellar and gaseous disk. So we take the time scales as an input and calculate the ellipticity of the halo, which the overall potential, which is practically spherical. So there's not much margin to make it flat. There were no simulations made in this context. We will do so at some point, of course. Because, of course, the self-gravity of the disk is very important in that question. It plays a large role that has been shown by Sparky and others, such that this can, of course, change the results. So, not taking into account self-gravity, we should come to the conclusion that this potential is towards the center, nearly spherical. So that's that.
Yeah, more or less. I was one of the authors actually who worked with HST data in order to resolve both NGC 4650 polar ring onto the stars and 2685. Yes, and we had a lot of discussion among the people who did N-body simulations concerning the stability of the disk for NGC 4650A that argued against our estimation of the age of a star, saying that it's impossible because the polar ring will not exist more than 10 million years. And they proved, well, based on the stellar content, we proved that at least there is stars as old as 100 million years, which contradict basically to N-body simulations. That's why I was so concerned if was any time frame estimation, for stability of the disks. This is completely two different galaxies. For 4650, it's hard to explain why it can be so long. For 2685, there is not really the polar ring. It's much more advanced or much more relaxed system. So I think. Okay, well, thanks.
We should talk about that.
More questions? So Dr. Jozsa will be with us for the rest of the afternoon. He will be leaving the ISC in the evening, so if you want to talk to him, he will be around, I guess. He is working at the computer center Sala de Usuarios, so you can find him over there. So let's thank our speaker again for